Hello, Sarah.
Hi.
I hope I have better luck with you than I had with your brother. I had to reboot my computer in the middle of our session. Hope that doesn't happen. That's happened with you and I before, if I remember correctly.
Yeah, well, you know.
All right. So you have special. What are you working on in class these days?
Okay, so right now we are doing inverse trig functions,
Okay.
and like phase shift and
Okay.
that. Yeah.
The sinusoid function. That can be, yeah, the sinusoid function being this. You might use different variables than C and D, but most everybody uses A and B. Have you studied this?
Yeah, that's what we're doing now.
Okay. And in other words, trying to figure out how to graph, say, hold on one moment, say 2 sine of 3 times x minus pi over 4 plus 5. How would you graph that? That kind of a problem. And they want you to be able to graph that, and they also want you to be able to read any graph you see and come up with what the sinusoid function is. And this can be some fairly complicated stuff. And then it really gets hard if they incorporate word problems, like tides, the tides going in and out, breathing, musical frequencies, daylights, temperature over the course of a year. All of these things follow some equation that can be written as a sinusoid equation. All right. Do you have some specific stuff?
Sort of. Okay. So I have one problem from today, and then a couple problems from a thing we learned a day ago that I think would be good to go over.
Okay.
Okay. So this is just talking about the inverse tangent.
Okay.
And it wants to find it's increasing, decreasing behavior.
Okay.
Symmetry, boundedness, extrema, asymptotes, and end behavior.
Okay, and we're talking about y equal inverse tangent of x.
Mm-hmm.
Okay. First of all, let's graph y equal tangent of x. Okay. It's one period of y equal tangent x. So if I'm going to create the inverse of this, I have to reflect that about the line y equal x, and I will have my inverse graph. And it will look something like that. Now, whenever you are graphing inverse functions, the domain and range switch. In other words, when I'm talking y equal tan of x, the domain is what?
Well, x is an element of all real numbers except for its asymptotes.
Well, except for its asymptotes, exactly. In other words, if I'm looking at the red graph here, then every pi, it's going to have another graph like that. And so x can be anything except a multiple of pi over 2, an even multiple of pi over 2. okay, because this is 3 pi over 2. So if I'm talking the inverse function, the green function, the domain and range switch. Okay? In other words, the range on the tangent function is negative infinity to infinity, right?
Yeah.
Okay? So the domain and range of the inverse tangent function, the green, well, the domain would be negative infinity to infinity. And the range is going to be whatever the domain was for the tangent function, which is all reals. I don't know how you write that, if that's okay, except x not equal to, let's see, it can't be minus pi over 2, it can't be pi over 2, it can't be 3 of pi over 2, so odd. I think that works, doesn't it? Yeah. Have you learned this kind of notation?
Yeah.
Okay. Where n is a subset of all real integers only. So in other words, n can be 0, which means it can't be equal to pi over 2, which is correct. N can be 1, which means it can't be equal to 3 pi over 2. N can be 2, which means it can't be equal to 5 pi over 2. So this is exactly correct for the range of the inverse function. Okay. And if I'm labeling the axis for the green function, then the x-axis is going to be labeled in numbers and the y-axis is going to be labeled in radians. So I'm going to have the pi over 2 right there if I am in green. And this point here would be minus pi over 2. Okay? Now, conceptually, let's just make sure we understand what inverse function means. And I'm going to switch it to sine just for clarification. If the sine of 30 degrees equals 1/2, by definition, the inverse sine of 1/2 equals 30 degrees. These two things are if and only if. If one is true, the other is true. And notice what's going on here. We take trig functions of angles and we get numbers, ratios. We always are taking inverse trig functions of ratios in order to get angles. Okay. So it's important to realize when you take a trig function, you're taking a trig function of an angle, and when you take an inverse trig function, you're taking an inverse trig function of a number to produce an angle.
Yeah, it's like when you're solving, you use the function called the angle and the angle to find the
Yeah, in other words, if I say the tangent of 45 degrees equals 1, and it doesn't really matter whether this is in radians or degrees, I could also say the tangent of pi over 4 equals 1. Well, by definition, that means the inverse tangent of 1 equals pi over 4, or 45 degrees. Now, what else did they want to know besides domain and range? Upper bound, lower bound, did you say?
Yeah.
Well, clearly the upper bound is what? Well, now let's go back and talk about something else here.
Okay.
When you are talking inverse trig functions. If I'm looking at a couple periods of the sine curve, and I want to talk about the inverse trig function here, well, if I reflect that whole thing over the line y equal x, which is how we get inverse trig functions, I'm going to get something that looks like this, which is not a function. Notice that it fails the vertical line test.
Yeah.
So, in order to cure that problem, mathematicians restrict the domain on the trig function, which is y equals sine of x. This is x, this is y. They restrict the domain such that it's 1 to 1. And in this case, that's pi over 2 minus pi over 2. If I talk about only that part of the sine function, then I do have an inverse sine function that looks something like, not real good at drawing these, but I'll try. I don't know if I did that right or not. Let's see. Yeah, not bad. Close. Okay? But I can only talk about the inverse sine function in between minus pi over 2 and pi over 2. And that's why if you go into your calculator and you say, what is the inverse sine of 30 of 1/2, you get 30 degrees. In other words, it gives you the answer that is between minus pi over 2 and pi over 2. Notice it does not give you 150 degrees, which is the second quadrant answer. 150 degrees is in this area right here. Okay? So the calculator is only going to give you the principal value for the inverse of the function. It's not going to give you all the values in the unit circle. It's going to give you, if this is positive, it's going to give you a first quadrant angle. If it is negative, it is going to give you a fourth quadrant angle. Notice that part that I just circled is the fourth quadrant.
Yeah.
Okay? And it will actually, if I said, what is the inverse sine of negative 1/2, it's actually going to give you minus 30 degrees, which is still a fourth quadrant answer. But it doesn't give you the third quadrant answer, even though the sine of 210 degrees is still negative 1/2. Your calculator doesn't give it to you. Your calculator only gives you the principal values because of this convention that mathematicians have adopted that breaks up, restricts the domain of the sine function so that you can talk about the inverse as being a function.
Why is it so important to talk about it as a function?
That's a very good question. That's an excellent question. I'm not sure I can answer it. I guess because you want to always be able to have a unique answer for the inverse function. In other words, when I say what's the inverse sine of 1/2, I know it's 30 degrees. Well, it's also 150 degrees. It's also 390 degrees. It's also 510 degrees. All of those are correct. It's just they're not the principal ones. Notice that I only want one value of y to exist for various x's. I don't want 4 values for y. Or
so it's like
go ahead.
Oh, so it's like a theory thing, and not like those other numbers don't have actual value mathematically, but they're just...
They do. If
like
you go into your calculator and you type the sine of 510 degrees, it'll give you 1/2. But if you go in and you say, what's the inverse sine of 1/2, it only gives you one answer. It doesn't give you multiple answers, even though there are an infinite number of answers. So if we want to deal with it mathematically, we really want one answer. We don't want all of these answers over here. So it's not a good answer to your question. I will say one thing, and that is that you're familiar with polar coordinates?
Uh-huh.
One of the major advantages of polar coordinates is they do not require this restriction for things to be functions. You can deal with relationships a lot better in polar coordinates than you can in XY plane coordinates. And that's also hard to explain, but it's as good as I can do at the moment. Okay, so that's for the sine. Well, the same thing with tangent. In other words, tangent has to be restricted to the first and fourth quadrant in order to even talk about its inverse. Notice that if I draw the tangent, that's minus pi over 2. That's pi over 2. As long as that's the only period I'm talking about, that's 1-to-1. I can reflect that and come up with the inverse tangent function. If I include more periods of the tangent, I can't do that. Now when I draw the inverse function, it looks something like this. Those aren't functions. The only way it's a function is if I have only one period of it plotted. And likewise to the sine function, if you go into your calculator and you type inverse, we know that the tan of pi over 4, 45 degrees, is equal to 1. So if you go in and you type inverse tan of 1, you're going to get 45 degrees, or pi over 4, depending on whether you're in radians or degrees. Okay? You're not going to get 225 degrees, even though the tan of 225 degrees is equal to plus 1. That's a true statement. But when you're talking the inverse tan, your answer is always going to come in the first quadrant or the fourth quadrant, just like sine. So if I say the inverse tan of 1, I get 45 degrees. If I say the inverse tan of -1, I get negative 45 degrees, which is a fourth quadrant angle. I don't get the second quadrant. Okay? So, when we're looking at the graph of the inverse tan, it doesn't really look like that's reflected over x equal y. It looks like this. We're just looking at one period of it. So it's bounded on the top by pi over 2. It's bounded on the bottom by minus pi over 2. Its domain is all real numbers. Its range is minus pi over 2 to plus pi over 2. And we don't consider additional periods. We only look at one period. And it's this specific period. In other words, they could have broke sine up into, they didn't have to break sine up into minus pi over 2 to pi over 2. They merely had to find a pi interval that would make it 1-to-1. They could have gone pi over 2 to 3 pi over 2. But they established a standard to go from minus pi over 2 to plus pi over 2. For the inverse functions of sine, tangent. Now, cosine is a little different. Cosine, notice the regular curve looks like this. Well, if I want that to be 1-to-1, I'm going to restrict the domain from 0 to pi. In other words, just this area right here is 1-to-1. And so when I draw the inverse cosine curve, it looks like that, something like that. I'm not very good at reflecting these things over that line. I'm terrible at it, in fact. That's probably not what the cosine inverse curve looks like. But you get my meaning. In other words, we need to restrict this original function to an interval that is 1-to-1. And if I restrict it from 0 to pi, it's 1-to-1. Notice if I use the same interval I did for sine, if I went from minus pi over 2 to pi over 2, it wouldn't be 1-to-1, because the cosine curve looks like this. So if I wanted to go from minus pi over 2 to pi over 2, I wouldn't have a 1-to-1 function. And when I flip that thing, I'm not going to have a function. So if I want to keep it as a function, then I have to restrict its domain. And in the case of cosine, they restrict it from 0 to pi. In other words, this part right here. Flip that over that line, and you have something that I believe looks like kind of like this. In other words, it should be, well, I don't know. We could look that up or whatever. You can find a graph of the inverse cosine curve. But that's the essence of inverse trig functions. Now, did we answer all your questions about the inverse tangent?
Yeah.
Okay.
Well, actually, I have a couple of,
What else besides domain, range, upper and lower bounds?
yeah, end behavior it has.
The end behavior? Okay.
Yeah.
The end behavior is always as x goes to either positive infinity or negative infinity. What happens to y, there's y, as x goes to positive infinity?
Okay.
What happens to y?
Y gets, it increases.
No, it approaches that asymptote. What asymptote? That's pi over 2.
Yeah. So you'd say as x increases, y approaches pi over 2?
Yeah. Y approaches pi over 2 as x goes to positive infinity, and as x goes to negative infinity, y approaches minus pi over 2.
Okay. Okay.
All right. What else you got?
So for my other things, it's just practice from a couple days ago I didn't get to. So I want to do sketches of graphs.
Okay.
So this one wants to sketch the graph -3 sine, and then the b value is pi over 2x, and then plus pi
Where's the parentheses?
after the pi. So
Where's the
pi
first parentheses?
after or before pi over 2.
Okay. That's important.
Yeah.
Because that affects the phase shift. In other words, is there another thing that's added on to the end?
Yes. Oh, actually, no. That was
Okay. So we have y equals that. Okay. So let's go through our letters. If we can figure out what A, B, C, and D are, we can graph it. What's A?
-3.
Okay. What's B?
B is pi over 2.
what is our period based on that?
So 2 pi over 2. And 4x.
Okay. What's our C?
Okay. This is the problem. This is the part I have trouble with. So it's C over.
Well, first of all, what's C?
Pi.
Okay. And what is the phase shift?
Negative pi. Well.
It's when you're in this format where B is inside the parentheses, this is not the phase shift. You have to factor out the pi over 2 and get it outside the parentheses. So I need to divide both of these things by pi over 2 and make it look like this.
Okay.
And this has to be 2. In other words, if I rewrite your equation this way, I haven't changed it. Notice that if I distribute it, it's the same thing. Right?
Mm-hmm.
Now, this tells us our phase shift. Our phase shift is minus C divided by B. When, it depends on the school system you're in. There's 3 different standard general formulas that are used. One is sine of, it's A sine of B outside the parentheses times x minus C. This is my favorite because this one, C, is the phase shift. Okay? But when the B is inside the parentheses, you have to get it outside. So there's another form that is this, in which case the phase shift is C divided by B. And there's a third form.
Okay.
There's this form. And when you have this form, the phase shift is minus C divided by B. So you have to be very careful here what the form of your sinusoid function is, how they give it to you. It depends. All 3 of these are significantly different because all 3 of them, it affects the phase shift. It doesn't affect the period. Notice that when B is inside the parentheses or outside, the period stays the same. The period is always 2 pi over B. But depending on which of these 3 you're using, the phase shift is different. In this case, the phase shift is minus, because it's a plus.
Mm-hmm.
And minus phase shift means we move to the left. It's a horizontal shift to the left. Okay? So, we don't have a D, so we don't have to worry about that. So all we have to worry about is how to graph this thing. And let me go down to here. I'm going to make this 3, this minus 3. Okay, to figure out how to graph it with a phase shift, start with the phase shift. Move 2 units to the left.
Okay.
That's where I'm going to start my sine curve. Now, how long's the period?
We decided it was 4.
It is 4, yeah. Okay? That means between those 2 points, I've got to draw a sine curve that goes up to 3 and down to minus 3. So the first thing I do is quarter it. by quartering it. I break it up into fourths, and now I know where all my key points have to hit. Okay? If there was no negative sign in front of the A, this would be relatively simple. I would start it here. I would go up to my maximum at that quarter point. I would come back down to there. I would go down to my minimum at that quarter point, and I would come back up to there. Okay? The only difference between this function is we're dealing with negative. This negative sign right here means that everything is reflected over the x-axis. So if I draw this in green, I'm going to start it here. I'm going to do everything exactly the same. I'm going to go down to -3 at that quarter point. I'm going to come back up through 0. I'm going to go up to +3 at that quarter point, and I'm going to come back down to my end of my period. Let's erase the red one because we were dealing with the negative, and there's your answer. There's your graph.
Okay.
Now, if there is a D involved, or whatever letter you call it, do you call it C and D in your general format?
Yeah.
Okay, good. If there's a D involved, it's real easy. You just shift everything up or down by D. In other words, if I were to add a +4 here, then the whole curve just gets shifted up by 4 units. And instead of going from -3 to 3, it would go from 1 to 7.
Right. Okay.
So the 4 things, or everything you can do to the sinusoid function, is the same as the translations that you did with polynomials. There's no difference. You can either shift it up or down, left or right. You can stretch it or squeeze it up or down. You can stretch it or squeeze it left or right. And you can reflect it over the x-axis or about the y-axis. And all of that can be done in this sinusoid function right here. There's your vertical stretch factor. There's your horizontal stretch factor. Oops, excuse me. C is your horizontal stretch factor. B is your horizontal shrink or stretch factor, and D is your vertical shift. So each of these letters merely do the same thing that the translations did in polynomials.
Cool. Okay.
All right?
Okay.
All right.
Thank you.
I will talk to you next Tuesday night, Sarah. Have a nice week.
All right.
Bye-bye.
Thanks.